So, as I said, we have 4 interesting presentations today. And the rule of the game is as follows. The presentations will be short. They will only be 10 minutes long. So they're a bit like a pitch where the researchers will present the work done so far. Afterwards, there will be time for 1 or 2 clarification questions. And at the end, we have reserved about 20 or 30 minutes for a broader discussion and a Q&A. So those are the rules of the game. Regarding the order of the presentations, we will go according to how the projects are presented on our homepage. And I've put the link in the chat as well. So you can look into more details and even contact the researchers who are working there. And the first one on our list is Emissions, Visualizations, Action, EVA, led by Professor Timo Göschel, who is also here with us this evening, and his colleague Alexander Dangel, who will hold the presentation. So without further ado, Alexander, the floor is yours.
Thank you, Alex. Just give me a minute to share my screen here. So, can you see my screen and can you hear me? Great.
Okay.
So, thank you, Alex, for the introduction. My name is also Alex, Alexander Dangel. I am a PhD student with Timo Göschel at the Chair of Environmental Economics. I would like to present our project Emissions Visualization Action, or EVA for short. We're a team of environmental psychologists, physicists, and economists who are working on this project at the intersection of novel technologies for visualizing emissions and behavioral change. So, as I just mentioned, we have a number of different work packages that are targeted at different new exciting technologies for visualizing emissions. So we have satellite remote sensing, we have facility scale imaging, and we have personal air quality sensors. Kind of like, well, exactly like the one I'm holding in my hand right here. These are small portable devices. I'm going to be telling you a bit about our part of the project, which is work package 3, which deals with the demand for such personal air quality information, before passing it on to Andre Butz, who is going to talk a little bit more about work packages 1 and 2. So we're taking our research to a very, very interesting part of Europe, and that is southern Poland. So we're looking at 2 regions specifically, that is Silesia and Lesser Poland. These are provinces that are quite urban and they are highly populated, and they happen to feature a significant number of greenhouse gas emitters, as well as very poor air quality, typically in the winter months. So overall, we think this is a great test bed for testing how different visualization techniques might work from the physical standpoint, as well as testing how providing this information to citizens might affect their mental models of pollution and its damages. So to take you a little bit into our work package at the Chair of Environmental Economics, we're going to be looking specifically at the demand for this type of information, taking personal air quality sensors as kind of our go-to example. And what we're really trying to understand from the economic perspective is how high is the native demand for such personal air quality information. So what we want to do is we want to see what is the general population interest in such a technology, and how much are people willing to pay for this. Secondly, we're interested in who it is that would adopt such a device. Are these particular socioeconomic groups? Are they groups that are located in certain neighborhoods or locations that might be affected by certain emitters? And maybe how does the demand for this information interact with information that is already provided, for example, by the government? we're going to be testing how monitoring incentives affect the usage of these devices and how people continue to monitor over time. And finally, we're going to want to see if providing this information actually stimulates environmental action in particular citizen groups. So we've developed this research design that begins with a direct mailing campaign for a device like the one that I just showed you, one of these personal air quality sensors. And as economists do, we vary things. So we're going to vary the offer price experimentally, and we're going to see how the demand increases as we lower the price. So as there may be a tipping point at which the demand for such devices increases. And we're going to be gathering information from households using online surveys that are directly connected to this mailing campaign via QR code. And there we're going to pick up information about socioeconomics, air pollution beliefs, their willingness to pay for such a device using methods like this multiple price list here. And then once households purchase and enter our study, there will be an 18-month data collection phase. Part of this will be a 6-week treatment phase where we want to see if paying individuals to collect this data actually stimulates their engagement with it. Finally, we're going to bring that all together and with an online end survey where we're also going to be testing if we can, if using these devices has stimulated some sort of a desire to engage in environmental action. Now, we piloted this, this research design just recently, a couple months ago in March 2022. And there we mailed 10,000 envelopes to households in Silesia and Lesser Poland that contained a pamphlet and a letter explaining this technology and an offer. Now, here on the right in the map, you can see where these households were. And what happened is that we actually had a very low response rate on this mailing campaign. And we actually have not had any sensor lottery winners yet. I didn't fully explain the sensor lottery, but long story short, we haven't deployed any sensors. But what we did find out is that the logistics of our research design do in fact work. But unfortunately, this was just a week after Russia invaded Ukraine. So we believe specifically in the southern Polish region where many refugees were entering the region, there were simply more important things on people's minds than responding to our letters. So we're a little bit frustrated and disappointed about this, but we hope that the situation will calm down a bit, hopefully soon, so that we can rerun this pilot when interest in air quality demand rebounds. Now, that's all from my side, from the demand for information. I'm going to now pass it on to Andrei Butz, who will present on the first two work packages. Thank you.
All right, thanks, Alex. So I would just ask you to go forward when I'm done with the slide, right? Okay. Yep. So in the other two work packages, we are looking at kind of coarser scales than the citizen scale. So, and using both ground-based and satellite-based Earth observation methods. And we started out here with, I would say, the currently best available satellite data set on greenhouse gases on regional scales. And again, we are looking here at the same region. The red dots that you see in all these four pictures are the methane exhaust shafts from the coal mining activities in the USCB, in the Upper Silesian Coal Basin. So there is a few dozens of coal mining shafts, and all they ventilate the methane that comes from the coal mining process from underground into the air. And what you see here is, as a color code, it's the methane concentrations measured by the satellite. It's called the Sentinel-5 precursor. It's the most modern European satellite that can do that. And you would see that for some episodes, you actually see like an enhancement of reddish colors to the southeast of these coal mines, and that is potentially the methane coming out of the mines. So this would be a visualization of the largest methane sources in the region, and could also be used in the future for confronting citizens with it. However, of course, the resolution here is not yet hyperlocal. And that's just because, I mean, the satellite has been launched in 2017, but you would expect that this is kind of a precursor study for what will be available around the year 2025 or 26, when we will have satellites that have much finer ground resolution and that can potentially detect these exhaust plumes with very fine-grained resolution. And then we can also zoom into more local scales also to confront people with. So what we did here for zooming in, and that's the next slide, Alex, we actually set up a model that can model the methane coming out of these out of these shafts, and that is shown in the upper picture. So this is now the red and the blue. These are, let's call it air trajectories, essentially the air coming out of these coal mines and being transported to the southeast, to the southwest here. And well, this is an episode where we have deployed ground-based measurement devices. These are the diamonds. And red means that the trajectories hit our southern instrument, and blue means that they hit our western instrument. And using this modeling and the measurements together, we were able actually to derive facility scale emission rates. And this is shown in the lower panel with the bars. So essentially you see here 6 exhaust shafts with Polish names on it. And we were able to update the emission estimates for these shafts. So essentially the gray bars are what we knew prior to our measurements, and the colored bars are our estimates for the new emissions. Of course, one needs to be careful because this is episodic, so this is only a couple of days, while typically the reporting is done on a yearly time scale. But nevertheless, we demonstrated the methods, and we were able to actually zoom into the facility scale with the help of our model and our measurements. And the next slide shows that the next generation instrumentation that we want to deploy. So we have a field campaign planned for June this year. There are some uncertainties also because of the war in Ukraine and the refugee situation down there. But we hope to be able to do it actually in June. And there we would deploy our hyperspectral camera. So that's shown on the left picture. And this camera essentially delivers 2D pictures of greenhouse gas plumes. And one of these measurements for CO2, not for methane in this case, is shown in the middle panel. So in this photograph overlaid with the red plume. And this is the CO2 exhaust plume from the power plant in Mannheim. Yeah. So essentially this was a test deployment for our measurements in Poland. And that was quite successful. And we have also set up a simulation that can model these plumes. And by comparing observation and simulation, we can again estimate the facility scale emission rates. And we have a PhD student that is currently working on that. And for the campaign data that I showed on the slide before, we actually have a publication which has been recently accepted and should come out any day now. Well, and so for the future, near term, we plan to do this campaign in Poland, and we hope it works out despite the refugee crisis. We have some change in personnel. So on the management side, we are probably not able to use all the funding that we have been granted, but we will need to discuss that later, maybe with Alex, how to mitigate this management problem. All right, so that's it for me. Thanks a lot.
Okay, thank you very much, Alex. Thank you, Andre, for this very interesting presentation. I want to congratulate you for doing this tremendous work despite the circumstances. I think it shows that no matter how much you plan, you never know the unknowns, but I think you've been very versatile, and given the circumstances, you've made very good advances. I would like to open the floor now for 1 or 2 clarification questions. You can either raise your hands or simply open the microphone and ask directly. So please. I have one hand raised from Thomas. Thomas, please go ahead.
Yeah, very short. Thanks and for this presentation. I think that's a very clear perspective. On the other side, you both mentioned the adverse effects of the situation in Poland. And as we probably all tend to anticipate that the situation there won't change within the next weeks, within the next month, and could even extend further. So do you have a plan B in case that you don't find or that you cannot observe any improvement on the ground with respect to the limitations that are put on your project from the effects of war refugees at this moment?
Should I start?
Go ahead. Yeah.
So yes, I mean, we actually think we can do it in June. Let's say if nothing dramatic happens until June, our partners in Poland are actually optimistic, and they actually want to do it. I mean, if not, it's mainly about these ground-based deployments, right? And then, of course, we would try to do more measurements at the coal-fired power plant. I mean, that would be in CO2. We could also try to address methane sources in the vicinity of Heidelberg, or maybe to reschedule somewhere else. Although for methane, actually, the USCB would be the best region, I have to say. Yeah, and of course, it also needs it should be in the same region as work package 3 and 4, right?
Okay, thank you.
Yeah, I mean, I can follow up on that as well a little bit. So we were very unfortunate that this was really, the week or two after the invasion happened, and this was really a shock for everyone, right, including us in Germany. And I know we were all thinking about other things at that time. So I think we have some hope that, later on there won't be the same shock, there won't be the same magnitude of people arriving in Poland. So maybe air pollution would be kind of a higher topic on people's minds. But yes, we are thinking, of course, about plan Bs. I think we would work, obviously, with across the work packages to ensure that there's a good spot that works for all of us, whether that's in Heidelberg, Mannheim, or maybe a region in like northern Italy that is a little bit more stable.
Okay, thank you.
Thank you. One more short question from Werner Eschbach. Werner?
Yeah, hello. I was wondering about the parameters that are measured. Probably in the remote sensing, it's methane and maybe CO2, it's already the greenhouse gases. But in these personal air quality sensors, what are they measuring?
So these do not measure greenhouse gases. They measure fine particulates. So PM1 to PM10. Yeah.
Okay.
But maybe just to put it into context, I mean, the reason why we're doing this, right, because essentially it's a proof of principle, right? I mean, it provides us with some idea about what will be happening with pollutants, which can be measured at a personalized basis, right? In some sense, it is kind of the most favorable setting to be observing demand for information. And so in this sense, it kind of helps us to benchmark what might be happening then with greenhouse gases.
Perfect. So for further questions, please contact Alex, Andre, and Timo directly. I would suggest we move on with the next presentation, which is from a bigger group of researchers. So it's LACHGAS, led by Professor Frank Kepler, together with Dr. Martina Schmidt from Environmental Physics, Lukas Menzel from the Geographic Institute, and Steffen Greiner from the Center of Organismal Studies. And this evening, we will hear from Martina Schmidt, which has already started sharing her slides with us. So the floor is yours.
So thank you for the introduction. And yeah, I want to present our project, the greenhouse gas nitrous oxide in the environment, and especially the laser spectrometric measurement of N2o concentration and isotopes in the field and in the lab to identify sources and quantify fluxes. This project is from Frank Kepler from the Earth Science Department, me from the Environmental Physics, Lukas Menzel from the Geography Department, and Steffen Greiner from COAS. So we are really a group of tackling, let's say, the nitrous oxide problem from different point of view. As nitrous oxide is not as common as greenhouse gas, let's say just a few basics. N2o is the third most important greenhouse gas after methane, CO2, but it's also an ozone depleting substance. It has a high global warming potential of nearly 300 times of that of CO2. And its concentration now is, since here's a plot of the last 1,800 years, and you see that in the 1800s it started to increase. And if you are looking today, it is nearly 333 ppb. So the increase rate since the pre-industrial time is 22%, and it has a long lifetime of 116 years. And it's responsible of 6.5% of the global warming. Just to give you a bit information on the sources and things, this is a global budget. And you see on the left side, the orange here, you see the anthropogenic sources, and on the right side you see the natural sources, which are the land, the soil is emitting N2o, but also the ocean. And if you look at the anthropogenic budget, you see that we have the agriculture, especially the fertilized soil, but also biomass burning, fossil fuel and industry, as well as other indirect emissions like from lakes. So we see large uncertainties in the fluxes. For example, if we take the agriculture sources, here a number of 4.1 is given, but it ranges between 2.7 to 6.3 unit is teragram of nitrogen per year. And there are many uncertainties, especially also in the emission factors, which are not well known due to also different soil management, but also changes in climate conditions from year to year. So what is also missing information about the fluxes, the N2o flux of permafrost thawing. So our project is on the high precision measurement of nitrous dioxide concentration and on the isotopes. Here is a N2o molecule. So you see, isotopes are built from atoms with different mass numbers. So you can have here an oxygen with a mass 16, but also the raw oxygen mass 18, which we note as delta O18, and the same is for nitrogen 15 or 14. So later you will see in the presentation delta 15, nitrogen alpha and beta, which gives also the position. So here our goal was to establish an innovative analytical technique to answer scientific question on the N2o cycle. We have the instrument. We have the instrument, and if we go to the next slide, this instrument can also be used to analyze samples. So here you see all the different projects we plan to do with this analyzer, starting with instrumental performance test, but also doing a study at Schauinsland Station in the Black Forest, where we will measure N2o isotopes in order to partitioning the emissions from the soil and also from a nearby adipic acid chemical company, let's say. There will be field campaigns to lakes and to wastewater plants. And here you see also a figure on the coarse plant chambers where we can do experiments using under specified conditions with plants to see how they emit N2o, like you see here also in this picture where plants are included in a class. But also there are two studies planned on permafrost, one in Mongolia and one in Greenland. So to see what we have done until now within the project, after we got the okay that the project was funded, we placed the order on this analyzer, which is really, let's say, one core of our project, and yeah, it was planned that it will be delivered in December or November, December, but due to problems at the manufacturing company, it was only delivered end of January, and we had beginning on February, we had it was installed at the Institute of Environmental Physics, and we had an on-site installation and training from one person from this company. During the last 3-4 months, we have done a lot of verification tests to see if the manufacturer specifications were fulfilled, and working on the calibration strategy, and did some field measurement in the atmosphere of Heidelberg. Here you see basically that the analyzer installed in our lab. We have here the analyzer, it's a cavity ring down spectrometer, and we have here a small sample module, which is an addition to allow us to work with smaller samples, collecting at the permafrost or where we want, and or also at plant chamber. And here is syringe to inject these samples as well. We have calibration gases, we have a multi-position valve, and we have an air inlet. So the main work until now with the analyzer tests was done by my postdoc Antje, but also by Moritz Schroll and Hannah Geisinger from the Earth Science Department. Here to give you a flavor, there have been many tests performed until now. For example, we have measured 48 hours the same gas, and you see here N2o, O18, nitrogen 15, nitrogen 15 alpha and beta, and also CO2, which is normally not measured with this type of analyzer, but we made it also available with a lower precision, but still making use of it. So in red, we can see here the performance of the analyzer. The red line is the specification which was given by the company before we ordered the analyzer. And then you see the yellow line was how our analyzer was tested at the company, and in blue what was tested in our lab. So we have here the variability of the 10 minutes averages. The measurement take place nearly every second, so we are averaging all the data to 10 minutes to get sufficient precision. And you can see that for all components we are much better than we were expecting before we bought, and for some measurements we are even better than the tests were performed at the company. So there have been a whole bunch of tests done. We have looked at the Allen variance to see what is the best averaging time. We checked the long-term drifts. We work on the temperature dependency to see also if we need to carry out only measurements in the lab, or if we can put it also somewhere where the temperature is more varying, stabilization time. Then there was a lot of work done by Antje, Moritz, and Hannah on the small sample module, which is quite not so easy to handle these very small samples with a high precision. Then we worked on the calibration strategy and also on the linearity and cross sensitivity. To summarize, or first the next step, so we can say that the first measurements were looking very well. We will finalize the instrumentation performance test and the calibration to international scale. Antje was applying with a small proposal to a transnational access, ATMO access, to get access to a N2o isotope lab. And this was accepted, and we get now also our link to the international N2o isotope scale. And yeah, we can now more or less continue with the field campaigns campaigns and the sample analysis. So here I have the milestones which we wrote in the proposal initially, and I think we are, even if the instrument was delivered with a delay, we are still in time within 1 or 2 months for the next deliverables. Thank you.
Thank you very much, Dr. Schmidt, for this very interesting presentation. I'm happy to hear that you're in schedule. We were a bit worried with the machine delivery, but like you said, it seems to work out, so we're very happy to hear that. We have time for 1 or perhaps 2 very short clarification questions. So please raise your hands. Dr. Schmidt, if you could maybe stop sharing your screen, please. I can see if anyone raises their hands. It's a bit difficult in Zoom sometimes. Questions? As always, Thomas is the icebreaker. So Thomas.
Yeah, sorry. Thanks for the presentation. Yeah, I'm pretty happy to see that even despite the delivery, late delivery, that you're really gearing up very fast now. I wonder, when you want to do measurements on the dynamic scale, let's say you want to address changes in N2o release or content in a certain airspace. I didn't understand, how long do you need for one measurement? And so what kind of time resolution can you deliver if you want to look for a dynamic shift, let's say, in N2o concentration? That would interest me.
The concentration, we can even look at the minute value, even maybe a 10-second value.
Okay.
It is sufficient precise. With the isotope, we need averaging time, let's say, to have a good value. I would average at least over 10 minutes, better 20 minutes to have a more precise value.
Okay, thank you.
Thank you for the question. Is there any other short clarification questions or remarks? I see Professor Kepler is also here. Maybe he wants to say something.
Yes, certainly I can add something, and very shortly, not too long, maybe 5 minutes. No, I'm actually, Martina did a nice job in showing what we have established so far, and I'm also quite happy because there were some problems to begin, delay of almost 3 months, and now to see how the workers, Antje, Moritz, and Hannah have performed the last months is very nice to see. And I'm really, I think the most of the people in the audience, they think it's an instrument, but this is a really novel instrument, and you never know what you get. You never know. And in the beginning, we have heard from other groups who are not very happy, but the system, luckily, it's performing currently very well, and the tests are very impressive. I can tell that. So we probably, I'm hopeful, if it continues in that way, that if they do the final test, we can go to real sampling in the lab and maybe in the field. So our campaign to Greenland is now, we are going there in June. It's confirmed to get samples, but also getting in touch with Steffen Greiner from the coast to get the plant samples set up. So I stop now. I think you might hear that I'm really, and I do not know all the data, but now Martina have given me an update. So I'm really happy to see how it has developed. And I was quite skeptical in the beginning, so that's all.
Thank you very much, Professor Kepler. We're also very happy it worked out, and we should say this instrument also enriches the portfolio of the University of Heidelberg. So it's nice that we now have this machine, so to speak, and most certainly we're going to come up with a lot of interesting data and a lot of good publications. So looking forward to that as well. Okay, moving on now to a bit of a more, I don't know, constructivist approach, should I say. We have our colleague, Junior Professor Rosa Lehmann, who's a representative of the project, and I hope I pronounce it correctly, Interacting Actors in Polycentric Climate Governance. And Rosa is working together with Jale Tosun, who unfortunately had to leave a bit earlier today, Johannes Glückler, and Oscar Loreda. So And I'm sure there's other PhD students, which names I don't know, but maybe Rosa will tell us more about that. But without further ado, Rosa, the floor is yours. Yes.
Okay, Alex, sorry. Can you see my screen?
Yes, but not full screen.
Yeah, okay, but you can see the presentation, or what should be the, what can you see now? Presentation.
Now we can see your the presenter modus. So.
Okay, okay, I'll do it the other way. So I might not look into the camera all the time. I hope you.
Now we still see the presenter modus, so
okay.
the one we can repeat.
Okay, and share. Again. Okay, I can. Now you still see the presentator mode? No.
Perfect. No,
it's perfect. Oh, cool. Okay. So maybe I start with some, because you talked about late deliveries. We started our project. That is a group of, in fact, 6 people, 4 PIs. You see the names on the slide. Of course, they're the ones who are directing, but the work is being done and clearly enriched by 2 doctoral students who are in this room today, Alejandra Irigoyen and Emiliano Levario. And we started, in fact, I would say, with Emiliano in October and Alejandra in December, because we had quite some severe visa issues. If you want to set up international team, I just have to say that because I spent minutes, if not hours, in conversation with embassies and bureaucracies. And this is something I think we have to consider as a university and as international research group, if you don't only confine international collaboration to Europe or maybe North America, but there you also have visa issues. So we started, and what the goal of the project, or also the idea of the project, is that we look at actors and how they interact in polycentric climate governance. So like you see the next slide now. So the background of the idea of our research is that in the last years, well, we all know the UN process and the more top-down process of climate governance, but there has been what in some strands of political science research has been called organizational innovation. There have been, or we have seen, the creation of transnational forums, that is platforms where different actors, state actors, business actors, also civil society, NGOs, global, international, transnational NGOs interact and promote exchange between state and non-state actors to facilitate a structure for innovation, learning, financing of projects that respond to, in one way or the other, to climate change. But we saw as a research group, and this is basically also the work of Jale Tosun, who is not in this room anymore, to identify a research gap, that we have a complexity of multi-stakeholder, multinational and multi-level coordination that calls for new conceptual models, and that we actually have to look inside the interactions of these actors. So of course there are these forums and we can get numbers, but what they actually do and how actors perceive the work they are doing there remains a research gap so far. So condensed, our research question is: how do transnational forums affect the creation, choice, and international convergence of climate change mitigation policies? And our goal is, and we're embarking on that endeavor, on that adventure, I would say, to conduct multi-level empirical analysis of different actor groups located. Primarily, we thought about Argentina, Chile, and Mexico. We sort of expanded our regional portfolio to identify their policy preferences, perceptions of policy measures, and effects of cross-level learning. But also we use a mixed methods approach. This implies that we have qualitative and quantitative research methods we use. I will come back to that later. And on a theoretical level or conceptual level, we develop or try to contribute to a model of polycentric climate governance. This is also what Jale also presented, I think, in the Heidelberg Bridge Colloquium in October. And we seek to contribute to that line of theoretization. Okay, so particularly, Jale Tosun and Emiliano Levario, particularly the work of Emiliano, has been concerned with getting data on climate forums, on the different, there are many. So Emiliano identified a lot. If you have questions on that, he's in this room, he will be happy, I'm sure, to answer questions on his work. We identified different members coming from different countries. And what you see here is that we have, we included Colombia, Peru, and Brazil in the data set because the data showed that actors from these countries are quite numerous in the fora. And you can see a clear tendency towards dominance of state members. Also, you can see that here that we have, according to the different countries, that the blue column of state actors is quite dominant, I would say, in the picture of the actor scenario. And this is the quantitative branch of our research. And then we have a qualitative branch, which is primarily the concern of Alejandra. And the idea is to take the data or to tie up to the data gotten from Emiliano's research and the research on the data set of global fora, and then look into a specific forum and see how actors interact. And we chose in the first step to look at the Global Convenient of Mayors for Climate and Energy. Here again, if you have questions, Alejandra will be happy to answer them. And the idea behind this, first, we see a lot of the dominance of state actors. First, we thought we could also include civil society actors, but we saw that in many fora, if you want to have included all these countries, in some cases, in some, if not many, there's not much civil society in this fora. So we decided to look at state actors, the Global Convenient of Mayors. There's a research gap, despite the consensus that municipalities play a very important role in climate change mitigation and adaptation. But there is a clear research gap on municipalities from the global south, including Latin America, in these kind of forums, and particularly in the Global Convenient of Mayors. So we are interested in, the example of this forum can show its relevance, that we have local municipalities participating, but we have also regional sort of sub-fora. The region Latin America, it leaves out the Caribbean, is part of the Global Convenient of Mayors. And we have also some NGOs included in the Global Convenient of Mayors, such as ICLA, you might know, or C40, which serve as consultant or trying to facilitate networking. So we have multi-level and cross-scale interactions between state and non-state actors, and also tied to different level of governments or regional geographic scales. And how we work, we conduct interviews, we do participant observation. For example, there will be in Buenos Aires, there will be the World Mayor Summit, and there will be also some regional events. This can be done with online participation, but also in presence, being there. So we are interested in a few sets when we develop the interview guide, we're actually interested in how, from the perspective of the mayors or state authorities in the particular municipalities, how they perceive the process of this forum, how actually they work, what motivates them to participate or not participate, what are their preferred response to climate change, how they set priorities, what obstacles they observe, for example, financial obstacles, but also maybe resistance from some part of the local citizens, which positions are excluded and included, and at the end of the day, what kind of legitimacy has this form of what we could group into the model of polycentric climate governance. Okay, so the expected outcomes, despite a growing collaboration between, for example, the HCEs and also the HCE, we are very interdisciplinary groups, so we need to invest some time on trying to speak the same language. But of course, we envision some research findings, that we have some evidence on the networks, the communication and efficiency of transnational forums, that we have some results on conflicts, challenges, consistency and convergence of climate change mitigation in Latin America, looking at particular municipalities, and at the end of the day, a contribution to the theoretical model of polycentric climate governance. So that's it from my side. Thanks for your attention. And as I said, for the questions, I might direct to Alejandra and Emiliano.
Thank you very much for this very interesting presentation, Rosa. as the physicists would say, climate change doesn't care about political borders, but we've seen both in your case and in the EVA project's case, geopolitics does affect the ability of climate researchers to do good climate research. So I'm happy you managed to prevail and bring these two PhD students to Heidelberg. Also, warm welcome from my side to Emiliano and Alejandra. I hope I can convince you to join our HCE college as well. So maybe Rosa can help me a bit with that to promote our wonderful interdisciplinary.
I always promote the
HCE college. But let's open the room for one or two clarification questions to Rosa, Alejandra, or Emiliano. Anyone? Don't be shy. I'm still looking. One hand raised. And Thomas, the icebreaker. Thomas.
I'm sorry, but I'm just curious. Thank you for the presentation. I have a very fundamental question to the project, how it's going at the moment. You're focusing on Latin America, yeah, and when you think about trying to contribute to a theoretical model of polycentric climate governance, are you expecting that the principles of a theory of polycentric climate governance will be different in different large areas of the globe because of political boundary circumstances? Or do you think at the end of the day you will come up, or you hope to come up with some very fundamental insight that would probably hold also for other regions in the world? Yeah. So how much does a particular situation in Latin America contribute? What you're expecting from that?
Mm-hmm. That's a very good question. I think it's open to me. I can only give you my answer. Maybe some group members would have a different one. Well, I would say, and this is one of the strand of critique on polycentric governance, is that it's very Eurocentric in its assumptions, and also when we come to research. So one idea why we try to decenter this research, look at Latin America, was also because, as I said, in the case of the Global Covenant, there's not much literature about that. But I would assume that we could, let's start like this. So one of the critique I find most convincing, and this also comes from my background in anthropology and political science and development studies, that of course the context of concrete implementation of policies and how actually actors can behave, how they perceive, for example, global initiatives, of course this has to do a lot with context, and this sort of is validate for every world region. But I think the insights we get about different sets of obstacles, a variety of participation, how actors perceive that governance works, I think that could feed into an overall model of polycentric climate governance, which heavily needs to be decentralized. Mm-hmm. I don't know if it's a sufficient answer, but okay. Maybe in 2 years we can.
You will know more. Okay, thank you. Mm-hmm.
Thank you very much, Rosa, and thank you, Thomas, for the interesting question again. Looking at the time, I would suggest that we move on to our next and last presentation of this evening, and then have a bit more time later for questions and answers. So our last project is called, and it's quite a long title, so bear with me. You also see it on the slide. It's Generating High-Resolution CO2 Maps by Machine Learning-Based Geodata Fusion and Atmospheric Transport Modeling. Luckily, it has a very catchy acronym, Gecko, and it also has a very large interdisciplinary team of researchers, 2 of which will present this evening. And I believe the first one is Dr. Sanam Vadag, which is here with us. Sanam.
Thank you very much, Alex. Exactly. I will start, and I'm very happy to present you some first results of the Gecko project, which is a joint project of the Department of Geoinformatics and Environmental Physics. And as Alex pointed out, there are many people who contributed to these first results, which I will show today. So maybe to motivate the project, maybe let's just look at the CO2 emission map of the United States from an emission inventory called BRÜCKE. And what you can see immediately is that the major emissions stem actually from urban areas and from cities. And globally, this is about 70% of the CO2 emissions come from cities, anthropogenic CO2 emissions. And therefore, cities also, of course, are drivers of climate change, but also have a huge potential and responsibility to reduce emissions. And as Rosa pointed out, realizing this responsibility within the last decade, there were many city networks which formed, such as C40, Convent of Mayor, N2o Coalition, which try to push mitigation in cities. However, the challenge is that they, of course, need to know where to start mitigation measures. And here I show the figure from the recent publication of Jungmann et al. And it, of course, depends on who is emitting and where and why emissions occur. And this is actually where our project sets off. We work on generating reliable CO2 emission and concentration maps to match the needs of stakeholders and citizens. And with that, we seek to, on the one hand, provide stakeholders with information on inner city emissions so that they can design efficient mitigation measures. And on the other hand, produce information that mobilizes and motivates citizens for climate action. I hand over to Sven.
Yes, I hope you can hear me because I haven't said anything so far, but looks fine. How do we do that? The idea is to come up with an emission inventory that has, of course, attached uncertainty because we are not 100% sure about the location of the emissions and about if we capture the variability between the different locations of emission sources. Right. Still, we do have that as a starting point. This is where we specifically from the Department of Geoinformatics set up to capture that spatial pattern of emissions. And the idea now is to compare that with measurements at a few locations about the concentrations of CO2, what Sanam's group is doing, and to link those two aspects, so the spatial distribution of emissions and the concentration measurements at a few locations, there's the modeling of the atmospheric transport. So basically, when we have the integral of the emissions at the location of the concentrations are measured, and by that we can also try to improve, or say at the first point, to identify problems or uncertainties with respect to our location of the emission inventory, because we basically can look at the residual. So what we expect, what we should have, and what we observe, we might, or presumably there's a mismatch, and whereby we can link those two things and try to improve our method for estimating the emissions. Next slide, please. I'm keeping that short, but basically we have different sources of information. We have information about the location of emission sources. That might be things like industrial facilities, open mining pits or garbage pits. It might also be the location of roads, if you think about traffic emissions. It might be the location of houses, if you're talking about the emissions of households, for example, by heating. And then in addition, we have other factors that are typically just available at aggregated level. So for example, we might know at a city scale level, we could have information, for some cities we do have those, about the aggregated CO2 emissions at the city scale without any further spatial differentiation. And then the idea is to downscale that, for example, by using auxiliary factors like population density to get a bit of a finer spatial pattern. Next slide, please. I would like to show you some first results of one aspect we investigated so far, that is on traffic emissions. Of course, traffic emissions by cars is related to transport from A to B. It has to do with the road network. And our idea is to identify factors that, that describe the amount of traffic volume for the different parts of the road network. We started doing that for Berlin, basically for the reason that we had the best data with respect to observed traffic counts. We do have the same thing for Heidelberg, for example, but the data was less valid or less less suitable for our situation. But we definitely try to transfer the model later on to Heidelberg, because this is where Sanam and her group are measuring. To get the general idea across, we want to build a model that uses data that are, at least in principle, available everywhere, at least inside of Germany. And we are using the road network, and we are using an estimated quantity that describes the importance of a specific part of a road network. So basically, how important is a specific part of a road network for the traffic that we assume. And if that is high, the importance is high, we assume a lot of traffic going through that road segment. That would mean if we have an estimation of traffic volume and we could link that with emission factors that make assumptions about the composition of a car fleet, then we can come up with a first estimation of CO2 emissions by transport, by traffic on this part of a road segment. How do we estimate that importance? We use something that's called targeted centrality. Centrality basically of an edge in a graph, like this road network is, simply measures for a random route how likely it is that it goes through that road segment. But we know more than just that we assume a random trip, because we know where location is located, and assuming that location is one of a part of a traffic demand equation, we can use that. In addition, traffic needs to go somewhere, so it has a purpose. People want to go to work, they want to go shopping, they want whatever, spend their free time in a nice way, they want to go to a university, to a school. So it's interesting to know the distribution and density of points of interest of different categories, such as, for example, shopping malls, places where people work, and many more things. And with that distribution that we can also get from OpenStreetMap, like get the road network from, we are able to simulate traffic by simply generating a number of trips. And we can use that to calculate the targeted centrality. That takes into account the demand side with respect to the points of interest, how they're distributed in space, and population, how they're distributed in space. And with that, we created this first map of Berlin. It's a bit hard to see from a distance, but we have 4 zoom-in maps where the estimated amount of traffic volume has been used together with emission factors to specify or to estimate carbon emissions on average for the different road segments. And with that, I hand over to Sanam again.
Okay, thanks. Now to get from the emissions, which Sven just pointed out, to concentration, so something we can measure, we need to take into account the atmospheric transport. And for this, we use the Graal model, which we set up for Heidelberg. Here's maybe a map of Heidelberg, maybe you recognize it. And in a nutshell, we use the Gram model, which is a mesoscale model, which we here set up for a domain size of 20 × 20 kilometers on 100-meter resolution. And it takes topography and land use into account. And then nested into that, we use the Graal model, which we set up for a domain size of 12 × 12 kilometers with 10-meter resolution, so very high resolution. And of course, to take the flow around buildings into account, we of course also need the building shapes. And then if we want to also calculate the dispersion of the model, we of course also need emission to actually forward these particles in our transport model. We use this coupled Gram-Gral model in a so-called catalog approach to get a dynamic situation. So for many different wind situations, we calculate how the wind fields would look like. And then for every hour, we take the real observations and compare it to the simulated wind fields and choose the one which best fits. And with this approach, we can actually save computation costs, which enables to really look at long periods over a whole city. We have set this model up for Heidelberg, and I saw the timer which Alex gave me, so I will be quick on this. We have evaluated performance over 3 months. And here on the left side, you see the observations, and on the right side, the simulations. And in principle, you see a generally good agreement. So in particular, the model is actually able to capture valley channeling and street channeling. And also, if you look at a time record here for one station, the LUBW station at Berliner Straße, you also see that it captures the day-night differences. So the general pattern, and we're currently still trying to optimize some details and understand some mismatches, which we also see. And then also, very short, Alex, we have also used the model for a thought experiment. So we set up a toy inversion where we have placed a variable number of measurement stations in our Heidelberg model and analyzed how well they would be able to estimate citywide emissions depending on the number of stations which we implement in the model and the precision. And as we would expect, you get better results the more measurement stations you have and the lower the uncertainty. But this really gives us also a quantitative mean for network design. So we really know what is necessary to verify emissions with which uncertainty. And we actually also plan to refine these inversions and look at more possible network designs. And with that, I will just summarize that we have set up this emission inventory and urban transport technically and from a method-wise perspective. And we hope to actually with this already contribute to creating immediate and influenceable information to be used by stakeholders, city networks, and citizens. Thanks.
Thank you, Sanam. Thank you, Sven, for this very interesting presentation. Sorry for pressing you with the time, but as you can see, the fish is out of the water, so it dries up, so time is running. We would have time for one short clarification question before we move into the Q&A. So please open your microphone and ask directly. I see claps and one raised hand from Professor Kepler.
Yeah, very interesting. Thanks. I have a quick question. I think if you look at the location at the map of Heidelberg, you see on the left side the Rhine Valley, on the right side the forest. Yeah? So I would be very keen, I think, on your model to see currently when I'm in the forest, we see everything is getting green. So the vegetation sucks up a lot of CO2. Can you see how is your model, or do you already see an influence? I think that might complicate a lot the whole system, but could you say reflect a bit on this?
Very good point. Definitely, the biogenic fluxes are the big elephant in the room. And so far for the first part, which I showed, we really analyzed the metrology. So we didn't even look at CO2 fluxes yet. And for the inversion part, we can of course take whatever emissions we would like in our inversion as given. And what we do is that we play around with the degree of confidence which we have in our prior emissions. And this also could be biogenic emissions. And therefore, this toy inversion gives us actually a handle to play around with how would biospheric fluxes, which are highly unknown, influence our result. But at the same time, we have not implemented that yet. And this will be a huge chunk of work still to come.
Thank you.